So chapter 14 is about oscillations, which is just like wave patterns, things that move back and forth repeatedly, stuff like that. Equilibrium means we are in the middle, where we're kind of relaxed, you could think, or just kind of sitting there with nothing happening. We're not moving. We're just kind of hanging out. The equilibrium position, where the object that we're talking about wants to be naturally. Okay. So we have some vocab here. The oscillation is motion that repeats again and again. So something going around and around, like a bike tire on a bicycle, just goes around and around and around. So if you had like a bug on that bike tire as it was spinning around, every time that it has gone around one complete time, that would be the period. So the time to complete one full cycle is the period. And the frequency is the number of cycles that occur in 1 second. So per second is the units on that one. And we kind of talked about this before. So period, the amount of time it took for a pendulum to move back and forth one time, something like that. So we can talk about that as being an oscillation as well, because it's just moving back and forth over and over and over again. The units of frequency are hertz, so abbreviated Hz, and 1 hertz is 1 cycle per second, and so that is 1 s to the negative 1 power, or 1 divided by seconds. Okay? Yeah, an inverse second. So now the equilibrium position, like I said, is where the object wants to be at rest. So it doesn't have any forces acting on it, just wants to sit there. The restoring force is the net force that directs the object back to its equilibrium position. When we were learning about springs, we were talking about the restoring force. That is exactly what this is. Good so far? Okay. So, in figure 14.1 there, the equilibrium and restoring forces on a ball in a bowl. So you have a bowl, you let the ball go on the side of the bowl. It's going to want to roll down into the middle of the bowl, and then it has kinetic energy, so it's going to roll right back up the other side and get rid of all of its kinetic energy and turning into potential energy, and then it rolls back, okay? So depending on the amount of friction that you have, if you have no friction at all, that ball is just going to go back and forth forever. And so therefore, this is a oscillating situation, all right? Which means we can talk about that, we can talk about the period, the frequency, and all those things. So if I look at this first picture here, if I can find I cannot find my thing. Okay, so free body diagram of the ball in the original position. So here's the ball. We have obviously the weight down. We have the normal force, which is always perpendicular to the surface. So the normal force will be acting in that direction over there, but the normal force will be acting in that direction there. The weight is always directed straight down towards the center of the earth. So in this case, we have an F net looking like that. So for this ball sitting right here, the F net is in that direction. When we get down to the bottom, the F net is which way?
It doesn't exist.
Yeah, there is no F net here because the only forces that are acting on this are the weight down and the normal up, and they would balance each other out. So the F net is gone. But as soon as we start to climb up the other side, then the F net starts to come back. Okay. So the oscillating motion of a ball rolling in a bowl, figure 14.2 now, we can see that the F net is this way on that side, but then once we go up the other side, the F net is this way. And in the middle, we do have a velocity, but we do not have an F net. Okay, so common units for frequency, we talked about hertz already. Remember that to the third power is kilo, so we have 1 kilohertz, 1 kHz, and the period of that is 1 ms, makes milliseconds. 10 to the 6th power, that would be like 1 million. So the prefix for that is mega, so we have a megahertz there. A capital M Hz this time. And then the period of that would be 1 microsecond. The prefix micro is 1/1,000,000th of a second. Now we have 10 to the 9th power, so that's a gigahertz GHz now. We are used to gig prefix using like memory on your computer or on your phone or whatever. That makes 1 ns, the letter N there is nano, so we have 1 nanosecond. FM radio station broadcasts an oscillating radio wave at a frequency of 100 megahertz. What is the period of the oscillation then? So what do? First of all, what is period, I guess? Oh, there it is.
The time it takes to complete one full cycle.
True, and we know that period is also the reciprocal of the frequency, right? So the period is the reciprocal of the frequency. This 100 megahertz that they gave us right here actually is the frequency. So we have 1 over. Now, how do I write 100 megahertz?
Would it just be 100 million hertz? I don't know if we want to write it like that, though.
Yeah, so 10 to the 6th power makes mega, and we have 100 of that. So 10 to the 6th times 100 makes 10 to the 8th power. So this is 1 times 10 to the 8th power hertz. Okay, and if we kind of carry out the division, then this winds up being 1, technically I could say 1.0 times 10 to the negative 8th power what?
Second. Microseconds.
So the way I wrote it would be seconds,
Okay.
because a hertz is seconds to the negative 1, but it's in the denominator, so it flips and becomes just seconds. Now we want to make that some kind of a reasonable, better looking number rather than 1 times 10 to the negative 8 seconds, because nobody understands what that is. Of course, nobody understands what the next answer is anyway, but so 10 to the negative 8th, we're how shy? We're an order of magnitude shy of 10 to the negative 9th. And 10 to the negative 9th would be 1 nanosecond, but we're an order of magnitude shy of that. So how many nanoseconds do I have then?
0.9.
Do I have 0.1 nanoseconds or do I have 10 nanoseconds?
10 nanoseconds.
It's 10. So 10 nanoseconds. That's your answer. Okay. So we also have something called simple harmonic motion, and you're going to see simple harmonic motion repeatedly in this chapter. Wave oscillations, those types of things, have simple harmonic motion attached to them almost always. So we want to know what this is. It's just motion whose graph has the form of a sine or cosine graph. We know what sine and cosine graphs look like. We might need to recall what they look like, but we've seen them before. These are called sinusoidal graphs. So if you have a sinusoidal graph, one that has just a wave pattern to it like this, then this is simple harmonic motion. We can abbreviate simple harmonic motion SHM, and I will be doing that basically for the rest of the chapter. I want to recall for a second what a sine graph looks like and what a cosine graph looks like. So let me extend that this way a little bit. And then over here. So we'll do sine on this one, and we'll do cosine on this one. Where does a sine graph start?
You have 1.
Starts at
The origin.
the origin. And then it goes which way?
Up.
Up. So our sine graphs look like this. Okay? Where does our cosine graph start from?
That starts at 1.
This one starts at 1, so I'll put a 1 right here. And then which way do we go?
Then from there down.
Yeah.
To the
So we're
origin.
going to go down to -1, back up and down and so on. So down here, this would be -1. How high and how far down does sine go?
It goes to 1, then to the origin, then to -1.
Okay. Like so. Unless we have changed the amplitude, and then there would be a number in front of the sine function, and that'll tell you what the amplitude is. Okay, so the major thing that we have to remember is that sine graphs start at the origin and go up, and cosine graphs start at the peak and then go down. Okay? All right, so let's see. Examples of real-world things that have simple harmonic motion. So I have the classic problem where the spring is attached to the wall, and then there's a block attached to the spring, and we push the block in or we pull the block out. Either way, that block is going to want to move towards the equilibrium position. So if I take this block and I pull it out to here, now that block is going to want to go back because we have that restoring force. But it doesn't just go back to where it started. It goes back and then through where it started. So it ends up over here. Now there's a restoring force pushing it back towards the equilibrium position the other way. So then it starts going back the other way, but it doesn't just stop at the equilibrium position, it continues through it. So what we wind up with is this oscillating back and forth motion over and over until either friction takes it out or we stop it ourselves, because it will never stop on its own. So the mass oscillates back and forth through the restoring force of the spring. The period depends on the mass and the stiffness of the spring. So M and K. Okay, we also have vibrations in the ear. So this kind of neat little sketch in there is sort of how the inner ear works. Sound waves entering the ear cause the oscillation of a membrane in the cochlea, which is part of the inner ear. So the vibration can be modeled as a mass on a spring. That's why this problem right here is so important, because there's so much of our real world that can be modeled using that simple, basic harmonic motion situation that's going on there. Okay? So the period of oscillation of a segment of the membrane depends on the mass, again, and the stiffness of the membrane. There you go. It's the mass and the stiffness, just like with the mass and the stiffness of the spring. So now we also have the pendulum situation. So we take the pendulum and we pull it away from its equilibrium position, which would be right around there. It wants to go back, but it doesn't just stop there. It continues beyond. But now it has potential energy again once it reached its maximum height there. So it's going to convert that to kinetic. So it turns around and starts coming back. And it doesn't just stop there. It continues through until it loses all of its kinetic energy once again on the other side. So what we have is this back and forth constant oscillating motion. That's why a pendulum is also oscillating motion. Okay, so the period of the oscillation depends on the length of the pendulum and free fall acceleration, so gravity. If we're on a different planet, the period would change. Notice, interestingly, that it does not depend on what?
Mass.
It doesn't depend on mass, that's right. Okay, just the length of the bar or string or whatever, and gravity. Okay, motion of legs while walking. So we have these interesting giraffes here. The motion of walking animals' legs can be modeled as a pendulum motion. So earlier this year, I talked about how when a person walks, that motion kind of, is kind of circular motion. As the hip rolls over the foot, which is sitting right here, we have this acceleration towards the center of the circle, and we can kind of model that as circular motion, okay? Well, so what we're talking about here is the motion of walking animals' legs being modeled as a pendulum motion. So the rate at which the legs swing depends on the length of the legs and the free fall acceleration gravity. Again, the mass makes no difference here. There is a frequency or period that we could talk about with your legs. Okay? It's actually kind of interesting. So, two oscillating systems have periods T1 and T2. T1 is less than T2. How are the frequencies of the two systems related then?
So because period is the inverse of frequency, I think methinks like we could say that F1 is greater than F2.
So you think it's C? Okay. So we know that period is 1 over the frequency. Just as an example, if the frequency was 2 for period 1, sorry. If we had 2 here and 4 here, if I flip this around, I would have F equals 1 over T. They're just reciprocals of each other. So then the frequency for this first one would be 1 over 2. And the frequency for the second one would be 1 over 4. Well, 1/4 is less than 1/2. So that's why the answer is C. Okay? It was the other way around for period, but because we flipped them, the denominator becomes the thing that's the driving force here. So because we have a larger number here, that makes a smaller number here. The bigger the period, the smaller the frequency. Okay? All right. So that's the whole section.